It's very common on entrance exams for high school and especially for university. They give you a graph and ask you to determine which function corresponds to that graph, or the other way around, they give you a function and ask you what the graph of that function would look like. Whichever of those two things it is, students usually take a long time solving them, because what they usually do is start making a table of values. That is, they start plotting some points. And with that, they try to see what the graph would look like. You can do that, but the truth is, there are techniques to solve these exercises quickly. Really, almost instantly. In this video, I'm going to explain exactly that. How we can quickly identify what the graph looks like given a function, and the other way around, given a graph, we can identify which function corresponds to it. Specifically, I'm going to work with quadratic functions, so please pay close attention because we're going to talk about visualizing the quadratic function. Let's get started. Look, I've put a Cartesian plane here for you, and we're going to start by graphing the function f of x equals x squared. Only for this function, I am going to plot a few points, because I think it's necessary for you to really understand what the graph of the function f of x equals x squared looks like and why it is the way it is. Actually, the graph of the function f of x equals x squared is a parabola. Let's start building it. Look, I'm going to start by plotting, for example, a 0. So we calculate f of 0. That would be 0 squared because I'm substituting a 0 for x. And well, 0 squared is 0. Therefore, we have a point at 0, 0. Let's plot it. Now we substitute a 1, and that would be 1 squared, which is 1. So we have a point at 1, 1. Let's substitute -1 now, so f of -1 equals -1 squared, and that's equal to 1. In the same way, we calculate f of 2, which is 4, and we also calculate f of -2, which is also 4. So we have these 5 points. I could continue, but this will be enough for us to see that the curve would look more or less like this, right? Well, this is the graph of the function f of x equals x squared. Let's take it as a reference function, because from this one, we're going to make some shifts. We're going to make it a little wider, a little narrower. We're going to flip it. Well, we're going to do a lot of things to this graph, okay? So, let's continue. What would happen, for example? Let me erase this. And now I ask you, what would happen, for example, if we move this parabola, which is this black graph I have here, upward? For example, here. How would that affect the original function? Because the black graph, as we already said, its function is f of x equals x squared. But notice that now I'm shifting it 2 units upward. What would the new function look like? Well, it's very simple. The new function is f of x equals x squared plus 2. I want you to notice that. Let's put it this way. I'm adding 2 units on the outside. Let me turn on my little projector here, my laser pointer. There it is. Look, this plus 2 that I have here, well, what it's really telling me is that I'm shifting the function, or rather, the graph of the function, af, of x equals x squared, 2 units up. Let's say we're adding outside. For now, just follow me with that outside part, and in a moment, you'll see what I mean, okay? So if I add 2 outside, then I shift 2 units up. We're good so far, right? Simple. All right, let's erase this. And now let's think about what would happen if we take this same parabola, but now we shift it 4 units down. Start thinking about it, because if we just agreed that when we add 2 units outside, we shift the parabola 2 units up, then now, what do you expect would happen to the function? So, if now I'm shifting this parabola 4 units down, how would that affect the function f of x equals x squared? I mean, how would it look now? Very good. So now it should be f of x equals x squared minus 4, right? Because we're shifting it down by 4 units. And look, in fact, that's the new function. F of x equals x squared minus 4. Therefore, if I add outside, then I'm going to shift the graph upward. How many units? Well, whatever it says here. Here it says plus 2, so it shifts 2 units upward. Now, if I subtract outside, I'm going to shift the graph downward. How many units? Well, whatever it says here. Up to this point, all good, right? Perfect. Now, what would happen if I shift the graph, for example, to the right? In this case, I'm shifting it to 3. Well, look, it's interesting here, because now I'm not going to add. Here, one might think that since I'm shifting it to the right, I have to add, right? But it turns out that's not the case. It turns out that when we shift a graph to the right, we're actually going to subtract. We're going to subtract inside. What do I mean by subtracting inside? Look at how the new function would look. The original function, or the reference one, was f of x equals x squared. And I want you to see that now I'm writing x minus 3, all squared. Notice that this minus 3 comes from shifting my original graph 3 units to the right. So if I shift 3 units to the right, then I have to subtract 3 inside. Careful. Here by inside, I mean because it's inside the parentheses, see? Earlier I said we would call this outside. Notice that it's different, right? Here I have x squared plus 2, or I could have x squared plus 3. But I want you to notice that here we have x minus 3, and that's squared. Do you see that? That's why I'm saying we're subtracting inside. So if I move to the right, how many units will I have to subtract? Well, the number of units that I'm moving to the right. How much do I move to the right? I subtract. Now then, what would happen if I have, for example, the following graph? Notice that in this case, I'm moving 2 units, but to the left. Well, if I move to the left, then in this case, I would have to add. I know that here it sounds a bit contradictory, but right now we're going to check that what I'm saying is correct. So in this case, what would the graph of this new orange function look like? All right. So it would have to be x plus 2, and we're going to square that. In this case, since I'm shifting 2 units to the left, that means I have to add. Where do we add? Well, inside, right? It's different from when we did it over here on this graph. Well, on this function that's in green. Here we were adding outside, and notice that here we're adding inside. So that's different. I'll repeat, if I add outside, I shift upwards. If I add inside, I shift to the left. Don't forget that. That's very important. All right, I'll continue now. All right, what would happen if we have this new function? Sorry, with this new graph, I want you to see that in this case, we're reflecting it, or we're inverting it. So, what would the new function look like? Well, it's very simple. Now it would be minus x squared, so it's really easy. If I already know that the function that opens upwards is x squared, what would it be when it opens downwards? Well, it would be minus x squared. That's easy, right? All right, perfect. Let's continue. Pay attention to this. I'll show it again from the start so you can see clearly. Look, we're going to take this new function. Well, the same function, which is f of x equals x squared. And we're first going to shift it 1 unit down. Then we're going to shift it 4 units to the right, and then we're going to reflect it. The question is, what will be the function of this new graph? I'd like you to pause the video right now, think about it for a bit, and if you want, you can leave your answer in the comments below. What do you think the solution is? Before I tell you the correct answer, so think about it for a bit. Do you have it yet? Perfect. Let's see. Let's go step by step. Let's see. To begin with, we saw that a unit had shifted down, which means there has to be a minus 1 outside, right? Why? Because we are shifting it 1 unit down. Let me repeat it so you can see. Look, there it is. It shifted 1 unit down, so I have to put a minus 1 outside. Now, it's shifting 4 units to the right. What does that mean? Well, I have to subtract. How much do I have to subtract? Well, 4, right? Because it went to the right. How much do I have to subtract? 4 where? Inside. So for now, I subtract 1 to move down 1. Then I subtract 4 to shift 4 to the right. And then, what am I missing? Well, to invert, right? So that I end up with this. So, what does it mean that there has to be a negative at the beginning? Why? Well, because we're inverting the original graph. So, how would it look? Well, like this. Why? Because it was inverted. X minus 4 squared. Why minus 4? Because it shifted 4 to the right and then minus 1. Why? Well, because it went down 1 unit. That's it. It's done. As you can see, it's also very important to notice this here. We're using the vertex as a reference, so it's not too simple. I mean, what I'm really saying when I say I'm moving the whole graph is that I'm actually looking at the vertex, because in the end, what matters to me is where the vertex ends up. Look, if I notice that the vertex has coordinates 4, -1, then I'll know it moved. 4 to the right, so I have to subtract 4 inside, and it moved 1 down, so I have to subtract 1 outside. We agree on that, right? Perfect. All right, let's continue. Look. This graph I have here, this function I have here, which is negative open parenthesis x minus 4 close parenthesis squared, minus 1 is the one that corresponds to that graph I have there. But I don't want it to be just me who gets it. It's important that you can see that in fact, what I'm telling you is correct. So we're going to go to GeoGebra. Look, I already have it open here. There's no graph yet, nothing, because I want to do it here together with you. I'm going to start by putting my reference graph, which was f of x equals x squared. So I put x squared, there it is. Look, it's this one I have here. That's the graph of the function, f of x equals x squared. Now let's put in the other one. We already knew where it had to go, right? It has to be exactly the same. So we start by putting a minus. Let me see if I can put it with this. Yes. Actually, no, not this one anymore. Let me hit enter so it saves. Now it's good. So we put a minus, and we have to open parentheses. Here's the parenthesis. We put x minus 4, x minus 4. Then we have to move over, because we need to square it. And then we have to subtract 1, 1, 1. We hit enter, done. I want you to see that the graph of the function minus x minus 4 squared minus 1 is this one here in blue, and it has exactly the same position that we had. Right, let's check it again so you can see that. Indeed, it does have it. Look, the vertex is at 4, minus 1, and it's facing down. And that's what we have, right? 4, minus 1. And it's facing down. So like I was saying, what we did was correct. We're good. Right. Perfect. Now let's look at something else that's also super interesting, and it has to do with the coefficient of x squared. Look, let me move forward, and now we're going to quickly graph the function f of x equals 0.2x squared. I'm going to give it some values. Let's see. I'm going to evaluate the function at 1, 2, and 3, and also at minus 1, minus 2, and minus 3. When I do this, it gives me the following, and well, we can then draw the parabola. I want you to see how the graph is turning out at 3. Function f of x equals 0.2x squared. Please take a look at how it turned out. Because now I'm also going to graph the function f of x equals 0.8x squared. We do the same thing. We evaluate at different points, we get these points, and we draw our graph. I want you to analyze this. Look, when we have 0.2x squared, let me put it this way. My graph turned out a little bit wider, right? I mean, it expanded when we did 0.8x squared, like it got a little closer together. I mean, now it looks more like the reference graph or the reference function, which was x squared. So, when we have 0.1x squared, the graph is going to look like this. See how it's really wide? Then when we have 0.2, it starts to get narrower. 0.3x squared, it gets narrower. 0.4x squared. 0.5x squared. I mean, it's going to get narrower little by little until it gets to x squared, which would be more or less like this, like the one that's in black. Well, it turns out that if we have, for example, 2x squared, it gets even narrower, then 3x squared, 4x squared, 5x squared, 20x squared. So here the parabola is getting, but it's really narrow now, okay? So, if we have, for example, 0.1x squared, it would look like this. Then 0.2x squared, 0.3x squared, 0.4x squared, 0.5x squared. Are you following me? So, it keeps getting narrower until it reaches x squared, then moves to 2x squared, 3x squared, 4x squared, and continues narrowing. And look, as an example, I also graphed the function f of x equals 4x squared. As you can see, it would look more or less like this. Like I was saying, the larger the coefficient of x squared, the narrower it gets. Don't forget that. If the coefficient of x squared is negative, then it flips, and it's exactly the same. So, if I had, for example, minus 0.1x squared, then it would open downward, but very wide, right? Then if it were minus 0.2x squared, it would look like this. Then if it were minus 0.3x squared, it would look like this, and so on, right? So, if it were minus 40x squared, it would open downward, but really squished. Right, are you following me with that? So, what does the coefficient do? Well, let's see. As a summary, let me put this up for you as a summary. What does the a do? Which is exactly that coefficient. Well, the a will tell you if the parabola opens upward or downward. If it's positive, the parabola opens upward. If it's negative, the parabola opens downward. So the graph of the quadratic function now also tells you if the function, or, well, the graph of the function, it expands or contracts. Remember, it's wider. It's expanded when we have values between 0, and 1. So, whenever it's between 0 and 1, it's going to be a little wider than the reference function. So, whenever it's between 0 and 1, it's going to be a little wider than the reference function. If it's between 0 and 1, that coefficient, the value of a now, if it's greater than 1, then it starts to contract more and more, right? The larger the value of a, the more it contracts. And we said that with negative values, exactly the same thing happens, right? Now what about b? We said that with b. When we add or subtract inside the parentheses. Are we going to shift the graph to the left or to the right? When b is positive, the graph shifts to the left. When b is negative, the graph shifts to the right. So it kind of does the opposite, so to speak, right? And well, what about c? That one's really easy. If c is positive, the graph moves up by c units. If c is negative, the graph shifts down by c units. So, to sum up then, do we all agree on everything? Perfect. Simple, right? Now let's do a little exercise to see if you understood me. Once again, I put the reference function here for you, and now let me show you this new graph. Go ahead, take a look at this graph, and only with what I've told you, you have to tell me which of these functions this graph corresponds to. I would like you to pause the video right now and really try to solve it, if you want. Don't put the answer in the comments for now, because I'm going to give you homework in a moment. But at the very least, start thinking about what the correct answer might be. Start analyzing it, because obviously one of these has to be correct. So please think a little bit before I tell you the correct answer. All right, perfect. So let's see. Let's do a little analysis. Let's see. Right off the bat, I see that this graph is a little more stretched out than our reference function. Our reference graph, right? Because look, over here we have the graph of the function f of x, which is equal to x squared, which is, well, kind of normal, I'll say. And notice that this one here is a little wider, since it's wider. Does that mean the coefficient has to be 4 or 0.4? Well, not 4, right? Because 4 is kind of more squished, right? So those with a coefficient of 4, we're going to discard them. So it's not b and it's not d either. Now, quickly, right away, the graph goes upward. The fact that the graph, the parabola, goes upward means that a has to be positive. So the correct answer isn't option A either, right? Because I want you to see that here in option A, there's a negative at the beginning. And if there's a negative at the beginning, it's as if the graph goes downward. So that's not it. Therefore, the correct answer isn't A either. So the correct answer has to be option C. That's it. That would be the correct answer. But anyway, let's see if it matches with everything else. Let's see. 0.4 positive. It indicates that it's going upwards and that it's kind of wide. It's wide and goes up. We're doing well. Now this plus 3, meaning that we're adding 3 inside. It indicates that it's shifting 3 units to the left. Let's see. 1, 2, and 3 units to the left. See if the vertex is shifted. 3 units to the left. Now this minus 3 indicates that it shifted 3 units. 3 down the vertex or the whole graph if you want to see it that way. But use the vertex as a reference point to make it easier for you. And see that indeed, the vertex is shifted 1, 2, and 3 units down. Therefore, we can see that indeed, the correct answer is C, so we check it off. Done. Well, now I'm going to give you a homework exercise, so please review this. I'm giving you a function, and you have to tell me which graph corresponds to the function I'm showing you here. When you have the answer, please put it down here in the comments. I'll be giving a nice round heart to those who get it right. And well, that's all for today. I hope the video was helpful, and most importantly, that you enjoyed it. See you next time. Take care and behave. Bye.